Let's move on to our third way to hydrate an alkene, hydroboration oxidation. With hydroboration oxidation, it is our first introduction to the anti-Markovnikov addition. Notice how in this alkene, we have carbon 2 here is more substituted. Carbon 1 at the end of the chain is less substituted. And what we notice is that water is added anti-Markovnikov, opposite of what we had thought beforehand. So this reaction does not go through a carbocation intermediate. We also see over the reaction arrow that we have a quite different reagent. We don't have a Bronsted-Lowry acid, we have BH3. BH3 is a very, very interesting molecule because of the lack of octet for boron here. BH3 is actually a very good Lewis acid. It accepts electrons readily. Now, what happens in the solution of BH3, just so we can explain a little bit of what we see over that reaction arrow, BH3 actually forms a dimer. So in this reaction, we have a arrangement where two BH3 molecules actually start to share some of their hydrogens. Not only does this complete the octet, but it kind of just forms this dimer that locks our reagent BH3 into a diborane. Now, THF is a solvent. It's a polar aprotic solvent. It looks like this. It's a 5-membered ring where oxygen is one of those atoms. So it's aprotic. It doesn't have a polar proton, but it does have polarity to it. And what THF does to that dimer is it actually stabilizes our electrophile. It will break up that dimer in a Lewis acid base style reaction to create this electrophile. And that's the electrophile that we want. We want that boron to be reactive for us in this reaction because he is the first step. Notice how water isn't introduced until really the second step where we have peroxide and sodium hydroxide. Both of those would be in an aqueous solution with water. And so that's where water actually gets introduced. But the important part of the mechanism is actually in this first step. So let's go ahead and take a look at that first step. BH3 is going to be added across the double bond at the same time. This is called syn addition. And when things are added at the exact same time, I want to think about our starting alkene, and its stereochemistry is trigonal planar. So when BH3 approaches this alkene, the nucleophile, being the alkene, will attack our boron electrophile, and then hydrogen will come right back and form a new carbon-hydrogen bond. So boron to carbon, that bond is being added at the same time that the carbon to hydrogen is being added. This is syn addition. We're going to dive into the stereochemistry in just a little bit, but I wanted to make sure that we understood that one major reason why this is important to understand that these two arrows occur at the same time is because when we think about where the boron gets placed, that is where the oxygen is going to get placed at the end of the day. And so looking at where boron gets placed, he is actually being bonded to the less substituted center. So in this syn addition, the reason why boron gets added to carbon number 1 here, the less substituted carbon, is because of steric hindrance in that transition state. We will go through that transition state in just a little bit. Now, what happens is in this reaction, it's a lot of Lewis acid-base chemistry. We're not going to go through the whole entire mechanism in class. I'm going to show it to you. It's in the textbook. I want you to understand how this reaction works, but I would never ask you for this whole reaction mechanism on an exam. The first step, this one right here, is the reason for the regioselectivity that we see right here, regioselective. Boron gets placed on the less substituted center because of steric hindrance in our concerted reaction. And so when we're looking at that first step, this is the most important one for you to know. What happens after that is that each of these other BH bonds are going to react in the exact same way to pick up another organic molecule. Notice that this R group here is the exact same alkene that would react to make a trialkyl borane. What happens after that is a lot of chemistry, a lot of proton transfers and rearrangements occur. Let's just go through this so that we can see what happens. The peroxide and hydroxide in step number 2 react to do a proton transfer. The pKa of a peroxide of H2O2 is 11.8. The pKa of water, the conjugate acid of that acid-base step, is 15.7. So low pKa to high pKa, yes, this reaction happens. Then the trialkyl borane comes into the picture, and that peroxide does a nucleophilic attack on the boron. This is a Lewis acid-base reaction where the oxygen that is negatively charged will attack the boron electrophile. Boron, not having its full octet, can accept another electron pair. Notice the boron now gets the electron. Then we have a rearrangement occur. Now, this rearrangement is very interesting because what really happens is a loss of a hydroxide at the same time that a carbon group will migrate over to an oxygen, kicking out that hydroxide. Again, this reaction step is very difficult to truly understand. So I'm at that point where I want you to see how the oxygen gets added and notice that there is no way for that R group to rearrange itself, right? We're not doing a carbocation rearrangement. We are simply picking up a carbon group and inserting an oxygen. And this is the oxygen that will be the resulting OH group on our alkyl product. So I'm just going to highlight this guy right here, right? It's this high R group attaching to that oxygen. We do it 3 times so that all of those R groups get oxygens. Now, I'm going to press forward with just highlighting one of those oxygens. Now, hydroxide comes back to do another nucleophilic attack. And then that's where we have a loss of a leaving group. Our OR group is going to get kicked out so that we can create our final alcohol, right? At the end of the day, that's what we are making in this reaction. And remember that R group is our final product that we had up here, right? This R group now has a hydrogen on carbon number 2 and an OH on carbon number 1. So when we're looking at our hydroboration oxidation, what do I actually want you to be able to remember and do overall is this step. I want you to be able to take an alkene. Notice that in hydroboration oxidation, when we have BH3 and THF over the reaction arrow, followed by that peroxide and hydroxide step, that we are going to make an alcohol just like before. However, it's anti-Markovnikov. The H and the OH are going to be added to the positions just like BH 2 and H were added in this first step. All right, here's that transition state and understanding why the anti-Markovnikov addition happens. We've been labeling these carbons, carbon number 1 and 2. As the alkene starts to break and to react, not only is the boron added, but the H to boron bond is also breaking and adding to the alkene as well. So we don't have an isolated carbocation intermediate, but what we do have is a stable transition state that is anti-Markovnikov. The large group BH2 is added to carbon number 1 here because carbon number 1 is less substituted. If we thought about swapping those and putting the large group on the more substituted carbon, carbon number 2, notice that there's all this steric hindrance. These sterics cause high energy transition states. And so we again are choosing a regioselective reaction where boron is added to the less substituted side, and therefore the oxygen is added to the less substituted side in the final product. Let's go ahead and just try one more so that we can start to see that syn addition and what it actually means. So BH3, solvent THF there, just to understand the dimer does not form and we actually get a reaction happening. In that first step, I want to do it here for us to show again just that syn addition. Alkene attacks the boron. The hydrogen goes back to the more substituted side. I'm going to draw that intermediate right here, and I want to just add some stereochemistry. Syn addition, meaning that BH2 and H have to add not only at the same time, but at the same side. Syn addition, H and BH2 must add both wedged or both dashed. There's no way to orient those two groups being added at the same time on opposite sides, what we will later call anti-addition. Syn addition, when the reaction is concerted and both sigma bonds are being formed at the same time, that syn addition shows that the two sigma bonds being added are being added to the same side. Then we have our oxidation step with H2O2 and NaOH, and we simply replace BH2 for OH. That is the process that I would want you to understand. So we will always make syn addition products here with hydroboration oxidation. If chiral centers are formed, we form enantiomers, but they will always be that syn addition product where H and OH are added to the same side. So be very clear with that one. Another syn addition reaction is hydrogenation, adding H2 across a double bond. This one, we're going to again walk through a mechanism to show the syn addition, and we'll show the other reagents there. This needs a catalyst. H2 gas is a very tricky reagent. It has a pKa of 35, so a proton transfer with a carbocation again is not likely going to happen. And what happens in this reaction again is syn addition. I'm going to draw out and just kind of space out my alkene here. And I'm going to take H2 and actually write out H2 gas with the single bond. Pi bond breaks and attacks that first hydrogen. Because hydride is not a stable conjugate, that H adds to the other side. Again, syn addition, concerted reaction here. And so if we want to think about the stereochemistry of our product, which is a little simpler than hydroboration oxidation, but we see the same syn product where we will get H added to the same side, whether they are both wedged or both dashed. So with these concerted style mechanisms where there's really no intermediate, what we want to be able to say on those rate determining steps, the first step of hydroboration oxidation and this only step in hydrogenation is syn addition, concerted mechanism where the two sigma bonds are being added at the same time, they have to be added to the same side. We could get enantiomers, right? But there's no carbocation intermediate, so no carbocation rearrangements. And there is stereoselectivity. So when we're thinking about these reactions, syn addition is the stereoselective nature. Those two sigma bonds will always appear on the same side, never on opposite sides. This is a good idea to just understand what that PDC, this is a palladium on carbon catalyst. So imagine a sheet of graphite and some palladium impregnated inside there so that it can actually collect the hydrogen gas, and it collects the hydrogen gas and it also locates that alkene, right? And it coordinates those two so that they can find each other and react together. Usually one H is added at a time. However, the alkene is not released until that second equivalent of H is added. And so we can think of this still as syn addition, adding those two hydrogens at the same time on the same side. Palladium on catalyst or platinum or nickel are all really, really good catalysts to make this reaction happen. So you can see any of those under the reaction arrow or over the reaction arrow as the catalyst, and it would produce the same exact product.